Underflow is the quiet counterpart to overflow. Where overflow happens when values grow too large, underflow happens when values become too small to be represented meaningfully. A useful metaphor for underflow is measuring drops of water with a bucket. If the bucket has markings only for litres, then millilitres disappear. The water is still there in reality, but the measurement system cannot see it. Underflow works the same way in data systems. So what is underflow? Underflow occurs when a value becomes smaller than the minimum representable non-zero value in a given representation. At that point, the system can no longer distinguish the value from zero, and it is either rounded down to zero or treated as insignificant noise. Underflow is not about exceeding limits, it is about falling below them. How does underflow occur? Underflow most commonly appears in floating point representations. Floating point systems represent numbers using a finite number of bits for precision and scale. This means they can represent very large numbers and very small numbers, but only down to a certain threshold. Operations like repeated division, exponential decay, normalization, or probability multiplication can push values below that threshold. When that happens, the value may gradually lose precision, become denormalized, or abruptly collapse to zero. In some systems, this transition is smooth. In others, it is sudden and silent. Underflow can also occur in fixed-point systems, counters, and time-based measurements when resolution is insufficient to capture small changes. Why do systems allow underflow? Because infinite precision is impossible. Representations must choose a smallest meaningful unit. Anything smaller cannot be stored efficiently, compared reliably, or computed quickly. Underflow is the cost of representing continuous reality using discrete containers. In many domains, underflow is considered acceptable or even desirable. Very small values may be treated as zero to improve performance, stability, or interpretability. But this decision always comes with trade-offs. Underflow has several defining features. First, it is gradual. Values often degrade smoothly before disappearing entirely. Second, underflow destroys relative differences. Distinct values collapse into the same representation, usually zero. Third, underflow introduces asymmetry. Large values remain distinguishable, while small values vanish. Finally, underflow is often masked. Systems rarely signal that underflow occurred. The data looks clean, but information has been erased. The implications of underflow are subtle but serious. In scientific computing, underflow can eliminate weak signals, distort simulations, or bias results towards zero. In machine learning, underflow affects probability calculations, gradient updates, and loss functions, leading to stalled training or incorrect convergence. In finance and analytics, underflow can silently remove low-magnitude effects that matter when aggregated or compounded over time. In security and cryptography, underflow can weaken randomness, reduce entropy, or invalidate assumptions about numeric behavior. Underflow is especially dangerous because it feels harmless. Zero seems safe, but zero often means unknown, not absent. Professional data systems treat underflow as a design concern, not a numerical accident. They choose representations with sufficient dynamic range. They rescale values before computation. They use logarithmic spaces when magnitudes span many orders. Because underflow is not a failure of math, it is a mismatch between reality and the resolution chosen to represent it. And once a value becomes too small to exist in the system, its influence is gone forever.